We're going to look at some examples today then of using trigonometric identities to substitute in to enable us to do some integration. It's quite a rare event to do this, or it's a sort of event where you need to use it regularly to be able to see these substitutions, to see which one you've got to make. And because there's many different ways to try and integrate a function, and this is just one of them, is trigonometric substitution. So the hard part is seeing which particular substitution you're going to have to make. And we started looking at these last week. Here are some of the examples of the sorts of times you'd use a trigonometric substitution. If you've got cos squared x, you'd use a particular substitution, and so on. Tan squared x, and this is an interesting one that we'll come and have a look at. That one there, the board's going a bit weird, and so on. So what we'll do is we'll look at some examples of how we can use these substitutions, and then it's just a case of having reference to the table. So in an exam situation, you'd have the relevant trigonometric substitutions. You're not expected to remember them, but what you will have to do is to decide in a given question which one you're going to use. That's the hard part. Once you've got it, actually the substitution is the integration becomes quite easy, and that's the whole point of it, is to make my integration, or my integral I've got to do, look like a standard integral. So often when it actually comes to the integration part, all you do is write down the answer. So let's have a look at an example here. I've written down the sort of steps you'd go through here as we go along. So determine the integral of this. Sine to the 5 theta d theta. Well, we're going to look through this example. Yeah, we'll look through this example. So what you do is you're going to use a trigonometric identity, and what we do here is we recognize that sine squared theta can equal 1 minus cos squared theta here. So sine squared theta can be written as, and this is the trick, this is the bit that you wouldn't necessarily see. Look, instead of writing it as sine to the 5 theta, we write it as sine theta times sine squared theta squared. And if you look at that, that is actually sine to the 5 theta, because you've got sine squared theta squared gives us sine to the 4, times another sine theta gives us sine to the 5 theta. And why do we do this? Is because we want this. We want this sine squared theta in the bracket, because then we can make the substitution. Instead of sine squared theta, we write 1 minus cos squared theta, which is this identity here being used. And it'll become obvious why we do that in a second. So what we do is, whatever this is, if it's an odd number of powers for the sine theta, we just split it up into sine theta times an even number of sine squared theta squared in this case. So if it was sine to the 7 theta that we had to integrate, what would we write here? Yeah, that's correct. So in other words, this would become cubed. So I'd have sine squared cubed, which is sine to the 6, times another one sine to the 7. So the key for this then is to make this inside the bracket here sine squared, so we can make this substitution. And then what we do is, it seems a bit odd, but let's carry on and see how this helps us. If I now multiply out this 1 minus cos squared theta times 1 minus cos squared theta, which is in fact, if we do it down here, so what I'm effectively doing is I'm saying, right, 1 minus cos squared theta times 1 minus cos squared theta. So I'm going to multiply out those brackets. 1 times 1 gives me 1 minus cos squared theta minus another cos squared theta gives me minus 2 cos squared theta. And then minus cos squared theta times minus cos squared theta is plus cos to the 4 theta, which is what we have here. So we just multiplied out those brackets to get to that. Okay? But this is all, remember, times by sine theta, so sine theta goes in front. Now we multiply this out. sine theta times 1 gives sine theta times minus 2 cos squared theta gives minus 2 sine theta cos squared theta, and so on. And you might not see it immediately, but that now is an integral we can do because we've been doing integrations like this in the previous week. The reason why we couldn't do this as it stood by algebraic substitution was because making the substitution for sine theta, we needed cos theta that could then cancel out the thetas, if you remember. Now, by making this substitution, we've introduced the cos theta term to go with the sine theta, which means we can just use an normal algebraic substitution here to do it. And if we think back to what we've been doing in previous week, if we just take one of these terms, we just integrate each one in turn. So if we take, say, this one, so if I was going to integrate the minus 2 sine theta cos squared theta with respect to theta, if you think back to our algebraic substitution that we were talking about in the last couple of weeks, we take the minus 2 outside the integral, so that's sine theta cos squared theta d theta, and then we make the substitution u equals cos theta. So then we can write this equals minus 2 integral of sine theta times u squared d theta, because u is cos theta. And remember what we do now, we have to change this d theta to du, so we differentiate this, du by d theta. The integral, the differential of cos is minus sine, and so now we change these around, so therefore d theta equals du over minus sine theta. So now we can put this into the integral here, and we can say, so this equals minus 2 integral of sine theta times u squared times du over minus sine theta. And it works because these cancel. And the minus comes out with the minus there to make it plus, so it becomes 2 integral of u squared du, and that's easy, that's just u cubed over 3. So do you remember the algebraic substitution only works because when we make the substitution, the original variable cancels out. And if we go back to the right to the top, we couldn't have used that here because there's no cos theta to cancel out the sine theta. If we made the substitution u equals sine theta, it wouldn't work because we'd have this cos theta term in there. But by making this trigonometric substitution, we've introduced the sine theta and the cos theta together, so we can do this. So it's quite a clever little way. It's like trying to make this integral look like something we can do, and that's what we've managed to do by using this substitution. Hang on. Now, next example to look at is examples of this type, look, where we've got sine times cosine. So far, we've looked at sine, cosine. We can do those because we can make the substitution and then cancel one of them out. But what's different here is that actually it's not the same value inside the sine and the cosine. So far, we've looked at only situations where it's been sine theta and then cos theta. It's the same variable inside or the same number effectively inside the cosine and the sine function. Now we want to look at the case where they're not the same. And what we do is we use this substitution here. And I want to talk about how this works. We've looked in the past at these compound angle formulae, that the sine of a plus b equals the sine of a times the cosine of b plus the cosine of a times the sine of b. Compound angle formula. You might recognize it. It's something that we've looked at before. Certainly those of you who've done the BTEC with me will recognize this formula. And similarly, the sine of A minus B equals, there'll be a minus here, equals the sine of A times the cosine of B minus the cosine of A times the sine of B. Now if we add these together and add these sides together, we end up with the sine of A plus B plus the sine of A minus B equals, if we add these, we get sine A cos B plus sine A cos B is 2 sine A cos B, and the cosine terms disappear, look, adding them together. Now, dividing both sides by 2, we get, therefore, that the sine of A times the cosine of B equals a half of the sine of A plus B plus the sine of A minus B. Just from those compound angle formulas, we end up with this, and this is the one we use. Look, instead of trying to integrate something like this, the sine of one angle times the cosine of another angle, we turn it into this: half times the sine of the two angles added together plus the sine of the two angles taken away from each other, and they're actually easy to integrate. So if we go back to the problem, that's what's happened here. Look, we've turned it into the integral here of half the sine of A plus B, so 3t plus 2t, plus sine of 3t minus 2t, which becomes a half, taking the half outside the integral, sine of 5t plus the sine of t. And that's easy. Sine of 5 just becomes minus cos 5 over 5. So actually turns into a very straightforward integral to do by making that substitution. I really like that one. It turns something that is quite difficult to do into something very easy to do using this compound angle formula. So now let's look at another example which is very similar. We've got this time cosine. So I want to now look at the compound angle formula for the cosine and see how that can work, and that actually arrives at this standard. There's another standard substitution we make coming from the table. This one here, the standard substitution in this case, is this substitution here. But again, we could derive where that comes from. It's from the compound angle formula. So if I were to just start this one off, you maybe want to finish that off. So if we go to here, what are the compound angle formulae for cosine? The cosine of A plus B equals the cosine of A times the cosine of B minus this time sine of A sine of B, and similarly the cosine of A minus B becomes the cosine of A times the cosine of B plus sine of A sine of B. And following a similar argument to the one we've just been looking at, you could then show the identity that we use here. Correct, that's right. Again, add them together. In fact, this time we can get two. We can add them together, and that gives us one useful identity to use as a substitution, or we could take them away from each other and we get another useful one. So that's worth looking at both ways. And in this example, we're using the way where we've added them. Look, the cos of one angle plus the other plus the cos of one angle minus the other. So we've added them together, and that means we can make that substitution. So now we can see that the 2 and the half cancel. So we've just got the integral of cos 7 theta plus cos 5 theta. Easy, it's just this. And then we put in the limits. These standard results are used a lot. And examples of integrations using these standards of results will certainly come up. I'm not going to go into where these are derived from. If you're interested in looking at it in the textbook, they are derived, these. Quite an interesting exercise in integration and algebra in itself to look at how these are arrived at. What they're saying is that if I want to integrate something of this form with respect to x, then that's the answer. This is the solution. So that's a standard integral. So I'm not asking you to do anything if you get a problem like this other than just write the answer in this form, sine to the minus 1x over a plus c. Sine to the minus 1 means the angle whose sine is x over a plus a constant. We always add this constant at the end of the integral. So what's the integral of 1 over root a squared minus x squared? It turns out to just to be the sine of the angle, or the angle whose sine is x over a. An integral of the form root a squared minus x squared with respect to x, where x is a variable, turns out to be whatever the constant is squared over 2 times, again, the angle whose sine is x over a plus x over 2 root a squared minus x squared plus c. Quite a complex result, but you're not expected to do anything more than just write that answer down, knowing what a is. So arriving at it is not straightforward. Again, if you want to look at how it's done, look in the textbook. But using it is straightforward. You've just got to use that standard result. The only problem might be getting your integral to look like that, so that you can then make this substitution. Okay?
What does 1 over square root?
Well, good question. It's to do with making a trigonometric substitution. So if you look in the textbook, you'll see how that works. But it's a bit, it doesn't seem intuitive at first, does it? No. And the last one to look at includes the tangent function. So 1 over a squared plus x squared turns out to be 1 over a times the angle whose tangent is x over a. So unusual results, but they're quite a lot if you've got functions like this to integrate. So let's look at an example here. There's our standard result. Look, problem. Evaluate this. And as we were saying at the beginning of today, the skill is not in the integration, but recognizing it, that it's one of these types. It's one of this type of integral. Look, it looks like that. So all I've got to do is say, a squared is 9, so therefore a must be 3, the square root of 9. So that means that we can just say, okay, the integral of 1 over root 9 minus x squared just becomes sine to the minus 1x over 3 between 0 and 3. I just write down the answer and work out what that is. And so it becomes pi over 2 or 1.5708. So if you look at the question, it's 3 lines. So long as you recognize that that's the standard result you're having to use. If I look back at the table, you can see it at the bottom, look, number 10. And again, you'll get this table of results, or the ones you need anyway, in the exam. Yeah, it is quite straightforward, but that's because we've recognized that it's a standard integral and what it is. You know? Yes, that's where it might be difficult, to get it to look like that. And if you think about integration, that's what's been the problem all the way along. If you look at your table of standard integrals, the difficult bit is not using that table of standard integrals, it's getting a thing to look like one of those standard integrals, then you can use it. No different here. One more example. Similar look. We can recognize it. So this type, this one, evaluates the integral between 0 and 4 of this. So again, a squared is 16, so a must be 4, and we can plug a into that standard result and work out the answer. Okay, I want you to, in the new textbook or the old textbook, try these exercises, please. Exercise 179 in the old or 189 in the 2. And these may well come up in the exam, some of these exercise questions. So the use of these standard integrals is something that I will be using because they are important standard integrals.